All right, so to recap redox reactions, I'm just going to start with the definition of oxidation and reduction. Now, the two definitions that we're going to look at is in terms of electrons and oxidation state. So we know that in terms of so we know that in terms of electrons, oxidation is the loss of electron, and reduction is the gain of electron. And in terms of oxidation state, oxidation is the increase in oxidation state. And reduction would be the decrease in oxidation state. I want to say oxidation number. So in terms of definition, you can use electron or oxidation state if it is not specified. Now let us just quickly also look at how to calculate oxidation state. So I'm just going to put some examples on the board and you will work out the oxidation state quickly. Is anybody writing? I can erase this, right? Guess we all know this. So. So the first one, calculate the oxidation state of nitrogen in the nitride ion. And again, nitrogen in NO2. All right, so I will give you 4 minutes to calculate these oxidation states. This one, the one that is underlined. All right, anybody else answer for number one?
Is it plus 5?
Please repeat.
Is it plus 5?
All right, that is correct. You have it for number 2 as well.
Number is plus 4.
All right. And number 3.
Plus 7.
All right. Number 4.
Plus 7 as well, correct?
Correct.
And
And
plus 6.
all right. All right, so let us just quickly run through them. So remember, when you adopt the individual oxidation state of each atom, they must equal to the charge on the ion. So here, the charge on the ion is minus. So when you adopt the oxidation state for oxygen and nitrogen, it must equal to -1. So we know that the oxidation state for oxygen is always what again?
-2?
-2, right? So the oxidation state for oxygen is -2, and we have 3 atoms of oxygen. So it's the number of atoms times the oxidation state of that atom. Plus, and the only other element present is nitrogen, which is what we're trying to figure out. And we use X to represent that. All right. Now we know that 3 times -2, that is -6. So X minus 6 is equal to -1. X is equal to -1 plus 6. We end up with +5. All right. So that is how we ended up with +5 for our answer. Give you a few seconds to write if I write it. All right, so let us work KMnO4. So this one, we don't have any charge. So the answer must equal to 0. Again, the oxidation state for oxygen is -2, and we have 4 atoms of oxygen. And remember, we are adding each of them. So we are trying to find Mn, so that is X. Potassium is in group 1. And remember, any element in group 1 has an oxidation state of +1. All right. So 4 times -2, that is -8. And we know we still have +1 here. So we are trying to find X. So we are going to carry everything to the equal sign. So X is equal to, if you carry over +1, it becomes -1. Carry over -8, it becomes +8. So if you want to write -1 plus 8, or you could say 8 take away 1. Whichever way you do it, you will get +7. Right? So in Mn, it's +7. And by now, once you see MnO4 or KMnO4, you should know that it is +7 because you have been familiar with potassium permanganate and dichromate since CSEC. Right? So next one, Cr2O7, 2-. For those of you who have just joined us, the class is being recorded and it will be uploaded. All right, so this one again, we have a charge, -2. We have 7 atoms of oxygen. So that's 7 times -2. And we're trying to figure out the oxidation state for chromium. However, this time we have 2 atoms of chromium. So instead of just X, it must be 2X. 7 times 2, that is -14. We still have 2X. So we're going to carry over -14. It will become +14. And so 2X is equal to +12. Remember, we're trying to find X. So we will divide by 2. And so X is equal to +6. For NO2, it does not have a charge. So the answer is 0. 2 atoms of oxygen, 2 times -2 plus X. So X minus 4 is equal to 0. X is equal to +4. And the final one, which one did I erase? Yeah, MnO4 minus. So the final one is MnO4 minus. So again, it's -1. Charge on oxygen is always -2. 4 atoms of oxygen plus Mn, that's X. So it's X minus 8 equal -1. X is equal to -1 plus 8. The answer is +7. Right? It is going to be posted to the YouTube channel. This is the name of it. All right, so all the videos I do, I post them here. All right, so we have defined oxidation state and we have calculated a few of them. Now, the next part that we have to do is to balance redox equations, which is the more technical part of it. All right, so we're going to move on now to balancing redox reactions. And the example I'm going to start off with is the reaction between potassium permanganate and iron sulfate. Now, if you get these 2 compounds on the exam and you're asked to write a balanced redox reaction, you're not going to write this plus this. All right? You must know what is actually taking part. It is a redox reaction. So not every atom is taking part in the reaction. The reaction is actually taking place between the permanganate ion, right? So not the potassium, it is the permanganate. It is taking place between the permanganate ion and Fe2 plus. So even though you are reacting potassium permanganate with iron sulfate, the actual redox reaction is taking place between the permanganate ion and Fe2 plus. So these are the 2 reactants that you will be working with. All right. Now, if you get the equation, right? Sorry. So let me write the equation. So it's MnO4 minus plus Fe2 plus. Can anybody tell me what will happen? Or potassium permanganate, which type of agent is it? Oxidizing or reducing agent?
Reducing.
Reducing.
No, potassium permanganate.
Oxidizing.
Oxidizing,
Okay.
right? Right. So if it is the oxidizing agent, what do you think will happen to Fe2 plus?
It's going to reduce.
It is going to be,
Reduce.
all right.
Reduce.
So hold on. So potassium permanganate is the oxidizing agent.
It's going to be oxidized.
Oxidize.
Right. So all right, if potassium permanganate is the oxidizing agent and it is a redox reaction, which reagent is Fe2 plus?
Reducing.
Reducing.
All right. So this is the reducing agent. Now, what happens to oxidizing agent in a redox reaction?
It causes
Yes,
another element to be reduced,
No,
to be
itself,
oxidized.
right? And itself, it will be reduced, right? So that means at the end of the reaction, the permanganate ion should be reduced. What should happen to Fe2 plus since it is the reducing agent?
Oxidize.
Oxidize.
No, Fe2 plus, the only other oxidation state higher up for Fe2 plus is Fe3 plus. So if we know that Fe2 plus is going to be oxidized, then, and the only other oxidation state after Fe2 plus that it can go to will be Fe3 plus. So at the end of the reaction, Fe2 plus will be oxidized to Fe3 plus. Right? Does anyone know what is the color of a solution containing Fe2 plus ions?
Green.
Green, correct. And what is the color of potassium permanganate?
Is that purple or
Purple.
pink? Pink or purple?
Purple.
Something
Purple.
purple. Okay, purple.
And what is the color of Fe3 plus?
Brownish red or red brown?
Yellow.
Red brown color. It will have a reddish brown color. Close to brown. Right? So let's work with red brown. All right. Now, the permanganate ion in this reaction, it is going to be reduced from the +7 oxidation state to the +2 oxidation state. Now, in this state, it will appear colorless. All right. So that is why when you see that observation of the potassium permanganate going from purple to colorless, it's oxidative. So remember, these are transition metals, right? That means they have more than one oxidation state. And when they change oxidation state, they also change color. So in the +7 state, the permanganate ion, all right, it will be purple. When it is reduced to Mn2 plus, it is colorless. And Fe2 plus is green. The Fe3 plus state is a different color. So that is why we can use color change to know that our reaction actually took place. So this is the equation to start out with. Of course, it is not balanced as it. And whenever you have charges or ions, the state symbol, it must be aqueous. So if they had asked for an observation, right, we know that the potassium permanganate, it would be decolorized. So it will go from purple to colorless. So what would be the final color of the solution? If these two colors are the colors of your products, what would be the final color?
Red brown.
That is correct. Because this is going from purple to colorless, and this is going from green to red brown. So the final color would be a reddish brown color. All right. Now it's time to balance our equation. So just a second, let me mute that person. Right. So now we're going to actually look at how to balance our redox equation. So I'm going to give you a second if you haven't written this out to allow you to write it out. And then I will show you how to balance the redox equations. All right, so if you have friends who are not able to join, it's because that I'm only allowed 100 students in the class. So it's at 100, so no more will be able to join. So if anyone is texting, that's the reason why we can only take 100 students. All right, so yeah, that's why. All right, so let us balance the redox equation now. So when you're going to balance the redox equation, so first thing, we're going to separate these into two half equations, the oxidation half equation and the reduction half equation. So this, if you get this equation, you first need to identify what is being oxidized and what is being reduced. So which species is being oxidized here?
Iron.
Right. So we have Fe2 plus as a reactant going to form Fe3 plus as the product. And which species being reduced?
Potassium manganese.
All right, so we have MnO4 minus going to form Mn2 plus. When you are going to balance the equation, you are going to balance it in terms of atoms and then in terms of charge. So you balance a redox equation in terms of atoms and then in terms of charge. So how many iron do we have on this side?
One.
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 Right. So we have one on both sides, right? So the equation, it is balanced in terms of atoms. Now, are the charges the same?
No, sir.
No. That means we have to balance charge. Now, for a redox equation, just make a note of this. The charges on the right must be equal to the charges on the left-hand side. So when it comes to your oxidation half equation, you are going to make the charges on the products on the product side become equal to the charges on the left-hand side. So at the moment, we have +3, right, on the product side, but +2 on the reactant side. So that means we need to bring down +3 to +2. So how many negative charges do we need to bring down +3 to +2?
One.
One
One.
negative.
One electron.
Right, so that is why we would have one electron here, because +3 plus -1 is equal to what?
Two.
That is
Two.
correct. It is equal to +2. So now you can see that the charges on both sides of the equation are equal. So you're going to first balance it in terms of atoms and then in terms of charge. So all we needed to do was add one electron to bring the charge from +3 down to +2. And this equation is completed. Now let us go to the reduction of equation. How many atoms of Mn do we have on this side?
One.
And how many do we have on this side?
One.
Right. Now, how many oxygen atoms do we have on this side?
Four.
Four.
Seven.
Four.
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 Let me write it quickly. Right. So we have 4 oxygen atoms on this side, but we don't have any oxygen atom on this side. Whenever you need oxygen atom, you are going to add
water.
water. That is correct. So you balance oxygen by using water. So let us add water on this side. Let me just erase this part. However, when we add water, now how many oxygen atoms are present in water?
Two. One.
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 But how many oxygen atoms do we need?
Four.
So how many?
Four.
We need four
Four.
more.
That is correct. Now, when you add the water, right? Which other atom have we?
Hydrogen.
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 That is correct. No, we don't have any hydrogen on this side. So to balance hydrogen, what are we?
Add 4
We're going
hydrogen.
to add 8.
Right. We're going to add hydrogen
8.
ions. So to balance oxygen, we use water, and to balance hydrogen, we're going to add hydrogen ions. And since as we have 8 hydrogens here, we need to add 8 hydrogen ions on this side of the equation. So now we have balanced the equation in terms of atoms. Now we need to balance it in terms of charge. So the question is, what is the overall charge? All right, let us do it separately. What is the charge on the permanganate ion?
1.
1.
Okay, -1. What is the charge on the hydrogen
8.
ion?
Positive
8.
No,
Positive 8.
+1, right?
Yes, sir.
But we have 8 of it, so it is +8. So the total, so the overall charge is what?
7.
7.
7. Positive.
7.
Wait.
Positive 7.
+7. What is the charge on water?
0.
Neutral. Like 0.
Right.
0.
And what is the charge here?
+2.
2 plus.
2
So
plus 2.
2 plus 0, we know that is 0. Sorry, +2. Right, so what we need to do, also, remember now for the oxidation of equation, the charges on the right-hand side must equal to the charges on the left-hand side. Now for the reduction of equation, it is the opposite. We need to ensure that the charges on the left side of our equation is equal to the charge on the right side. So we need to bring down +7 to +2. So how many negative charges?
Add 5 electrons.
5.
Because +7 plus -5, that will give you +2,
Positive
2.
right? And the negative charge we're adding is in the form of electrons. And so we will have 5 electrons on this side. All right. So we have balanced both equations. And so now is the time. So the next step, after you have balanced both your equations, we are going to cancel our electrons. All right. Anybody know how to cancel the electrons? What
So
should
we're
we
going
do?
to add 5
Sir,
to
yeah,
the
You need to
oxidizing.
multiply
yeah,
the
multiply
oxidation
the
1
top
by
no
5.
the top reaction by 5, so it's equal.
All right, so we should multiply both equations by the lowest number possible that will make each set of electrons equal. So as the person said, multiply this one by 5. And what should we multiply this one by?
1.
Sir, we should
1.
1.
Right, that is correct. Multiply it by 1. All right. So I'm going to erase this. So that means 5, we're going to multiply everything in the equation by 5. And so you will get 5 Fe2 plus to give you 5 Fe3 plus 5 electrons. All right. And then this one, everything would stay the same. So it's the 5 electrons plus 8H plus MnO4 minus, do not leave out your state symbols. Right? What else do we need over here? Mn2 plus 4H2O. Right? And then all we need to do now is cancel our
Cancel out the electron.
right. And then we would write our final net equation. And in this equation, we're going to write everything on the reactant side from
Reactant side.
equation, right? So in the top equation, we have 5 Fe2 plus, that's just it from the top equation. Then we go down here, we have 8H plus MnO4 minus, and that should produce Mn2 plus 4H2O. Right? I don't have the space to put the same symbols.
Sir,
Alright.
so to the
Sir, could we have
Fe2
iron?
plus. The iron, you miss out the iron.
Yes, sorry about that. Yeah, thank you.
Sir, could we have started the equation with the potassium manganese?
Sure, it doesn't matter which one. Because all we're doing is combining both of them. Alright, so remember this. Fe3 plus 5 Fe3 plus the 4H2O. Alright, and that is our final net equation.
Sorry, state symbols.
I don't have this. Let me try and squeeze them in. All right, AKs. And liquid for water. All right, so let me give you one to try now from the PDF. So I'm going to do this. All right, is anybody writing at the moment? All right, I'm going to erase and put one on the board. for you to try. This one is from 2016. So it's the first question in the PDF file. All right, so that's the equation. That says the dichromate 6 ion reacts in acidic medium according to the following equation. And the first question it is asking, identify the ion responsible for the green color. Can anybody tell me? All right, before you tell me the green color or the ion, what would be the color change for this reaction?
Green.
Orange to green.
Orange.
Right. So it will go from orange to green. Now, in which state is chromium here? What is the
+6.
oxidation state? Right. That means when chromium is in the +6 oxidation state, that is why the compound will appear orange. Therefore, when it is reduced to the 3+ oxidation state, that is when it appears green. So it is the Cr3+ ion which is responsible for the green color.
Green color.
Right. So this orange it's +6. When it's green, it is +3. All right. Then now it says given that the sulfite ion, given that the sulfur, let me just put it on the board. And this is for 4 marks. And it's from the 2016 course paper. So I'm going to give you, it's now 6:54. I'll give you 5 minutes. I think 5 minutes is enough for you to write the balance equation. So just so that no one's making a mistake, it says given that the sulfite ion is converted to sulfate ion in the presence of water, deduce the balance equation for the redox reaction between the dichromate ion and the sulfite ion. In this reaction, the sulfide ion. So this should be your next equation. Your sulfide ion to sulfate. So that is your next equation. Sulfide to sulfate. This equation up here, it is already balanced. So your first job is to balance this equation, and then cancel the electrons, just like we did earlier, and then write a final net equation. So balance this equation, whatever electron you get here, cancel them, and write a final net equation. All right, and I will give you some time to attempt it.
Sir, are we going to get the half equation? Or we're supposed to write it?
No, you would have to write it, but they basically told you the half equation. Because what they are saying, right? They told you that the sulfide ion is converted to the sulfate. So remember, this is a redox reaction. So if they had said the dichromate ion is converted to the CR3 plus state, what that means, during the process of the reaction, this ion was reduced to the 3 plus state. So all you have to do, this is the reactant, this is the product, and then you balance the equation. So when they tell you that the sulfite is converted to sulfate, it means that this is the reactant and this is the product. So hence, where I did it, reactant, product. So all you have to do is just balance it now. One more thing, is this the oxidation or the reduction of equation?
Oxidation.
Oxidation.
How did you know? Just
Because chromium was reduced.
exactly, right? Let us say you did not know that chromium was reduced. What happened to this? Which element would you calculate the oxidation state for?
Oxygen.
No, oxygen is always,
Sulfur.
Sulfur. Sulfur.
so sulfur is in which state here?
Um,
Plus 4, sir. 4 plus.
plus 4.
All right, and it is in which state here?
Plus 6. 6 plus.
Plus
All
6.
right. So the oxidation state, it increased, right?
Yes, sir.
All right. So it was oxidized, right? So that's the next way of looking at it. All right, so you can go ahead now. Right. Do you want us to work it or I want a little more time? All right, I'm going to work it now. All right, so sulfur is already balanced because we have one on each. However, we have 3 oxygen on this side and 4 on this side. Let me just make some space. Right, so we have 3 oxygen here and 4 over here. So what should we do to this side?
Add
Times
water.
by 4.
All right, just 1 water. Just checking.
Yes, sir.
Yeah.
That is correct. Because we have 3 oxygen already, so we'll need 1 more to make 4. All right, so now that we add water, what should we add to this side?
2 hydrogen.
2 hydrogen. That
Two
is
hydrogen ions.
all right. So we have just balanced the equation in terms of atoms. So we need to balance it in terms of charge. And remember, this is our oxidation path equation. So the charges on which side must equal to the charges on the other side.
Right, must equal.
That is correct. So the charges on this side must equal to the charges on this side. At the moment, we have -2, right, plus 2 positive ions. So those would cancel at the moment. So at the moment, -2 and +2. So the overall charge is 0. On this side, we have 0. So -2 from the sulfide ion and 0 from water. So the overall charge is -2. So what should we add to this side to move it from 0 to -2?
2 electrons.
That is correct. 2 electrons. Right. So we have just balanced our equation in terms of atoms and charge. So what is the next step? So both half equations are now balanced. So what is the next step?
Combine them.
No, cancel the
The
electrons.
electrons.
We're going to multiply it
Get
by
more OH on the board. Someone was asking where OH come from. Just a second. Where did the OH?
Oh, it wasn't referring to that. Sorry.
Oh, all right. Right, so we need to get rid of the electrons. So we have 6 here and 2 here. So we can multiply this equation by which number?
3.
Right. And remember, we always use the lowest number possible. All right, so we are going to multiply this by 3 and this one by
1.
right by 1. So multiply by 1. Right. So that means everything for this will stay as is. So Cr2O7, 2 minus plus 14H plus 6 electron. All right, and then this now 3SO3, 2 minus plus 3 water. Two electrons. All right. No, so we have 6 electrons here and 6 here. So the 6 electrons can cancel 6 electrons. However, in this equation, so if you notice, both half equations, they have in water as well as hydrogen. When that happens, we need to get rid of the hydrogen and oxygen from one
Sir?
side of the equation. Go ahead.
The H was supposed to be 6.
Oh, yes. Thank you for that.
Sir, do we have to reduce it?
If we have to,
If we have to reduce the hydrogen and water?
yes. So the final equation, we're just going to have hydrogen on one side of the equation and water on the next side. So if you look at this equation, we have 14 hydrogens. On this side, we have 6. So we have more hydrogen here than this side, right? So we are going to remove the 6 hydrogen from here and also take out 6 from this one. So we're not canceling in terms of like the electrons where you have to make them become equal. So 6 hydrogen is here, we're going to remove 6 from this. And we have 3 water here. So we are getting rid of the 3 water and subtracting 3 from this. All right? So 6 hydrogen, we're taking away the smaller number. So our final equation, it should be Cr2O7, 2 minus plus. If I take 6 from 14, how many hydrogen ions do we have remaining?
6.
Right. So it's 8H plus 3SO, 3, 2 minus. We have gotten rid of the 3 water, so there is no water remaining. And then we have 2Cr3 plus. And remember, we took away 3 from this, so we should have 4H2O plus 3SO4, 2 minus. And that's our final balanced equation. So just remember, if I have hydrogen on both sides of the equation or water, subtract the smaller number from both equations. Then you will write the final net equation. Run through these steps again. All right. Let's do back this step quickly. All right.
So it's just where you add the water and
This part?
Like
Where we transfer the water?
so from you add water to the sulfide ion.
Oh, okay. All right. So remember, all right. So let me just clear up here. So this is how our equation started out. The sulfide ion being oxidized to the sulfate ion. So the first thing we need to do is balance it like a regular equation. So we balance it in terms of atoms. So 1 sulfur is on both sides of the equation. So sulfur is balanced. When you look at this side, we have 3 oxygen and 4 oxygen on this side. However, with redox equation, when you need to balance oxygen, you're going to add water. And if you look here, so we have 3 oxygen here and 4 over here. So on this side, we are short 1 oxygen. You are not going to put a number in front to try and balance oxygen. You are going to add water. So every time you want to balance oxygen, you add water. So because the oxygen is lower on this side, we add water on this side. So now each oxygen molecule have 1 atom of oxygen. So we only needed 1 more oxygen to bring up this to 4. So 3 and 1, that's 4. Now, when you introduce water to balance oxygen, you also introduce hydrogen atoms. And so now this side of the equation does not have any hydrogen. To balance the hydrogen, we're going to use hydrogen ions. And so, because you have 2 hydrogens here, that is why we add 2 hydrogen ions on this side. All right, so that is why we have water here and hydrogen ions on this side. Water is to balance oxygen. So if you need to add oxygen, you add it in terms of water. If you need hydrogen, you add it in terms of hydrogen ions. So 2 hydrogen is needed on this side. We add 2 hydrogen ions. So once this was completed, it was balanced in terms of atoms. So next we need to balance it in terms of charge. On this side of the equation, let's look at the charge now. Clearly, water does not have a charge. So that is 0. The sulfide ion, it has a charge of -2. Now, if you add -2 and 0, the overall charge is -2. If you come to this side, the sulfate ion, it has a charge of -2. The hydrogen ion has a charge of +1. But we have 2 hydrogen ions, so that's +2. So if you add +2 and -2, the overall charge is 0. So the overall charge on this side is -2. The overall charge on this side is 0. Now bear in mind that this is your oxidation half equation. And we have said that for your oxidation half equation, the charges, the overall charge on the right-hand side of your equation must equal to the overall charge on the left-hand side. The overall charge here is -2. The overall charge here is 0. So we need to add some negative charges to this side so that it can become equal to -2. So 0 plus -2, that is how we would end up with an overall charge of -2. And the negative charge are added in terms of electrons. So if you need 2 negative charge, you are going to add 2 electrons. And that is how we get the 2 electrons here. All right. So this equation, it has now been balanced in terms of atoms and charge. The charges on both sides are equal. So once you have balanced both half equations in terms of atoms and charge, the next step now is to cancel the electrons. And to cancel them, we need to make them become equal. You have 6 electrons here, and you have 2 electrons here. So if you multiply this by 3, it will become equal to 6. So you would want this now to stay as 6, and that is why we multiply by 1 electron. So if you multiply this equation by 3, you are not just multiplying the electrons, you are multiplying every species in the equation. And so that is why we end up with, so we're times the equation by 3. So that is why we end up with 3 sulfide plus 3 water to give you 3 sulfate plus 6 hydrogen and 6 electrons. And because we time this equation by 1, everything stays as is. So that step now, after you multiply everything, so that the equations become equal, I mean the electrons become equal, that is when you can cancel. So the 6 electrons cancel 6 electrons. Some oxidation reactions, they would have just had hydrogen ions in one of the equation and water in one. But in this case, we have hydrogen ions in both of the equation and water in both of them. Do we normally subtract the hydrogen and water? Only if they appear in both equations. So here we have hydrogen in the,
Sir,
yes?
sir, if we don't subtract them, will we lose marks?
Because the equation would not be correct.
Okay.
Yeah. So you have 14 hydrogen ions here at the moment and 6 here. So you always subtract the lower number. So you subtract 6 to get rid of it here. And you subtract 6 from this one. So when you're writing your final net equation, as we normally do, so you have your CR, the dichromate ion, not 14 again, because we have subtracted 6 from it. So it's now 8. So it's the dichromate ion plus 8 hydrogen ion plus the 3 sulfide ion. We have not included the water because water is in the reduction equation and it is in the oxidation equation. But it is lower here, so all of it is removed from this one. So that is why our final equation here, it does not have any water present. On this side, of the 2 chromate ion, not 7 water. Remember, we took away 3 from this as well. That is why you end up with 4 water. And what else? The 3 sulfate ion. All right, so no hydrogen ion is on this side. So our final net equation, it always just have water on one side of the equation and hydrogen on the next side. So once you spot them in both equations, just subtract them. So we can cancel water, electrons, and hydrogens. That is correct, but just remember, you only cancel water or hydrogen when they appear in both equations. All right. All right, let's do our next past paper question. So just go. Please repeat. Please repeat.
Sir, would we get any basic equations?
If you can get, I'm going to look for one for tomorrow. All right. I'm just going to work the ones in the PDF. I haven't seen any basic ones on the past papers, just acidic. But I will look for, yeah, I will look for a basic one online. All right, so if you're in the PDF file, let's just quickly go to the next reduction question. So on the second page, on page 2, the one with potassium permanganate. So on it says define reduction and oxidation in terms of oxidation number. And we know that oxidation is in terms of oxidation number is? Anybody can tell me?
Increase in oxidation number.
Right, and reduction is the?
Decrease.
The decrease.
Increase
Yeah.
in oxidation.
Right. And then now it says identify. Oh, let me put the equation on the board. So the question says, identify the role played by the permanganate ion. So identify the role played by the permanganate ion in the redox reaction above, which is this one. So what is the role being played by this ion?
Oxidizing agent.
Oxidizing
It is an oxidizing agent. And then it says, explain your answer in terms of oxidation number. So why did you say it is an oxidizing agent? In terms of oxidation number, explain your answer.
It is reduced from +7 to +2.
That is correct. So the oxidation number, it decreased from +7 to +2. So if it was decreased, it means it was what?
Reduced.
Right. And once it is reduced, we know it is which agent?
Oxidizing agent.
Right. So it's the oxidizing agent because the oxidation number decreased from +7 to +2, which means it was reduced. All right, good job. Then now, the next part of the question, it says an aqueous solution of potassium iodide. So this time we have potassium iodide. So an aqueous solution, let me put it on the board for you. It's not a long question, so let me just write it. All right, so this is the question. An aqueous solution of potassium iodide reacts with acidified potassium permanganate to form a red-brown solution. On completion of the reaction, it says identify the species responsible for the red-brown color. So on the exam, right? What is happening here? An aqueous solution of Ki. So Ki. Which of these are we really interested in?
The
Iodine.
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 That is correct. And this is I minus, right? So it's the iodide ion. Now, you said that potassium permanganate is an oxidizing agent. So if this is the oxidizing agent, and it is reacting with the iodide ion, and a redox reaction is taking place, what is going to happen to the iodide ion? If this is your oxidizing agent, this is which agent?
The reducing agent.
Reducing agent.
Therefore, it must be, right, it must be oxidized. So if your iodide ion is being oxidized, what will it oxidize to?
I2.
Iron 2.
Sir, can you repeat the question, please?
Iodine gas.
I2. Right. So the question is that an aqueous solution of potassium iodide reacts with acidified potassium permanganate to form a red-brown solution. Right? And the first part of the question is, what is responsible for the red-brown solution? It couldn't have been potassium permanganate because this would have changed from purple to colorless. But in figuring out the question, right, we know that it is the iodide ion. So even though it says potassium iodide, the potassium is really a spectator, right? It is the iodide ion that is taking part in the reaction. Now, if this is your oxidizing agent, that means this is your reducing agent, which means that this must be oxidized. If this is being oxidized, it is going from the ion to the molecule. So it goes from iodide ion to iodine. So if this was being reduced, it would go from I2 to the ion. So that is how we know to set up this equation. Now, we told you that you got a red-brown solution on completion. So on completion means you would have got your product. So your product is this ion, which is not a red-brown color, and I2. So it's one of these two that is responsible for the red-brown color. So it must be I2.
Iodine.
Right. Just a second. Right, so it says identify the species responsible for the red-brown color. So it would have been I2. Right. Then it says, given that the iodide ion reacts according to the following half equation. So let me put the half equation on the board. By the way, let me not put it on the board. What would be the half equation? Well, basically, put it on the board, right? But I want you to balance it. So
Excuse me, sir, which year paper is this?
this one, I'm not sure which year I cut it from. But I think it was before 2010. But I don't remember exactly.
Okay, sir.
Yeah.
So it's 2 iodine ions and then
Right, 2 iodine ions.
in the molecule.
Right, how will we end up with I2? Remember, it's a redox, it's a half equation, right? Redox half equation. So what is missing?
Nothing.
Nothing, you sure?
Or the charges must be balanced, right?
Depending on the charge.
Sir,
Will
it's
charge?
electrons
Oh, the electron. Right?
Right,
on the right
2
side.
electrons
on the right side.
plus 2 electrons.
So this being oxidized, it is giving up electrons to form I2, right? So it says, given the iodide ions react according to this half equation, deduce the balanced equation for the redox reaction between these two. So let us do that quickly. So this equation, it is already balanced, right? In terms of atoms, 2i, right? And we have -2 here and -2 on this side. Because remember, this does not have a charge, so it is 0. So we have 2 negative charge on both sides of our equation. So it is balanced in terms of atoms and in terms of charge. What should we do next?
Equate them in terms of
With
electrons.
electrons.
We should cancel them, right?
Cancel.
Well, not cancel. Right.
No,
So,
wait, we're gonna cancel them?
so before we
Multiply the
Sometimes-
top one by 2 and the bottom one by
Yeah.
5.
To equate
Right.
both of them.
that is right. So times the top one by 2 and this one by 5. Right. So 2, so we'll have 2 MnO4 minus plus 16H plus 10 electrons, 2 Mn2 plus 8 H2O. And then for this one, it would be 10I minus to produce 10 I2 plus 10 electrons. So if you notice in this equation, or in these two half equations, only this half equation of hydrogen ions and water. So there's no need to worry about canceling hydrogen or water, only when it appears in both of the equations.
Questions? That's balanced, correct? Like the iodine.
Right.
Is it?
This,
The iodine, like the
There's
10
like
ions
5, the
create.
iodine should be 5.
we
Yeah, 5 iodine molecules, right?
yes, hold on. Yes, sorry about that.
Okay.
Yeah, man. So 10 electrons cancel, 10 electrons, and then we will write now our final net equation, which is 2 MnO4 minus plus 16 H plus 10I minus, let me put in the state symbols. Okay. All right, and that will produce 2 Mn2 plus 8 water plus 5 I2. All right. And so that is our balanced equation for the reaction.
The iodine molecule is going to be aqueous or solid.
Aqueous, it's in solution.
Okay.
All right. So the next part of the question now, part C. Is anybody writing or everybody finished writing?
I'll finish.
All right, good. So the next part now, we have a table, right? So we have MnO4 minus and I minus. So we have two substances, X and Y. Get next marker.
Excuse me, sir.
Go ahead.
So how often our class skip? You know.
For often
Then
our
we
class.
yeah.
Well, I want to try to, I won't be able to do any, well, I'm going to do one tomorrow. I'm not sure of the time, but the the person I'm going to send the link, I'm not sure who you'll get it from, but I will just send it back. All right. But I'm not sure of the time. It's most likely in the afternoon, but I'm not able to say as yet. All right. So you can just probably look out for a link from the person that
Okay,
sent it. Yeah, man. All right. So I minus. And then we have our observation. So MnO4 is decolorized in this one, and it is also decolorized in this one. And for this one, with the iodide ion, we get a red-brown color. All right. So red-brown solution. And in this one, no visible change. All right, so the objective for this table, so compounds X and Y are tested for their reducing or oxidizing properties with the permanganate ion and iodide ion separately. And this is our results. So it says categorize X and Y. So we are supposed to categorize X and Y in terms of their oxidizing and reducing properties based on these results. So potassium permanganate, what kind of agent is it?
An oxidizing agent.
Oxidizing.
Right. Once a reaction occurs with potassium permanganate, the next substance would have to be acting as what?
Reducing
Reducing.
agent.
That is correct. So in both cases, the potassium permanganate was decolorized. That means it was what?
It was
What?
reduced.
Right. Once you see the color change, it means that a reaction took place, so it was reduced. So if potassium permanganate was reduced by both X and Y, what does that tell us about X and Y? They are what
Both
type of
oxidized.
That's the agent.
No, not oxidizing.
Oh,
Remember?
they're both reluctant.
Right. Yeah. So remember, the potassium permanganate is the oxidizing agent. So these two would have to be the opposite. All right. So X, so just based on these two observations, right? With KMNO4, we would say that X and Y are reducing agents. Now the I minus, right? So if you have I minus and you get a red-brown solution, right? Something happened to I. Was it oxidized or reduced?
Oxidized.
All right. So if I minus was oxidized, what kind of agent is it?
Reduced.
So this is oxidation, right? So if I minus was oxidized to I2, what kind of agent is it?
Oxidizing.
The opposite.
Reducing.
So remember, oxidizing agents are always reduced, and reducing agents are always oxidized. Right. That is why the oxidation state of Mn is always reduced when it takes part in a reaction. Right. So if I minus is oxidized, that makes it the reducing agent. Now, if this is the reducing agent, what does it make X?
Oxidizing.
agent.
All right. So that means X can act both as what?
Oxidizing.
Reducing and oxidizing agent.
Exactly. Did someone ask me to repeat?
Yes, sir.
All right. So we already know, right, that potassium permanganate is strictly an oxidizing agent. So once you saw that it changed color, it meant that X and Y were reducing agent. So in a redox reaction, how you know that a redox reaction occurs is when you get some form of visible reaction. You use potassium permanganate and it was decolorized from purple to colorless. That means a reaction took place. So we know X and Y are reducing agent because potassium permanganate is strictly an oxidizing agent. Over I minus, let's say we're not sure what kind of agent is it. What is the question? We're to categorize X and Y in terms of their oxidizing ability. So are they oxidizing agent or reducing agents? So what we are using to answer the question is the observation. So when you react potassium permanganate with X, it changes from purple to colorless. That means potassium permanganate was reduced. So X had to be a reducing agent, right? When you add potassium permanganate to a solution of Y, it was again decolorized, which means that Y is a reducing agent. Now, when you come to I minus, you haven't been familiar with I minus like how we know about KMNO4 being what? An oxidizing agent. But if you look at the observation, right, it says a red-brown solution was produced. The only way you would get the red-brown solution is if I minus was oxidized to I2. And if it was oxidized, that means I minus is a reducing agent because reducing agents are always oxidized. So the question now is, if I minus is your oxidizing agent, based on this observation, what would it make X? Would X also be oxidizing agent? It would have to be a reducing agent.
Reduce.
Sorry, not reducing agent.
It's been oxidized.
No, if I minus is your reducing agent, the next substance has to be the opposite. All right? So we know that potassium permanganate is an oxidizing agent, right? That makes X the reducing agent. However, we just said that I minus is a reducing agent. So for this instance, what is X?
Oxidizing agent.
Instance,
Sex is also reducing agent.
oxidizing agent. So look, when X is reacting with potassium permanganate, it is
Can
a
you repeat that again, please?
All right, so when X, so what you have to remember is that some substances can act as what? Both oxidizing and reducing agent. So when X was reacting with potassium permanganate, we know that X had to be the reducing agent because we know for sure that potassium permanganate is strictly an oxidizing agent. So once you react potassium permanganate with any substance and you see potassium permanganate change color, the other substance is a reducing agent because potassium permanganate is a known oxidizing agent and it's strictly an oxidizing agent, right? So once you see a reaction occurs with potassium permanganate, the next substance is a reducing agent. So remember also, whatever happens, so if oxidation occurs, the substance is the opposite. So reducing agents are oxidized oxidizing agents are reduced. So potassium permanganate being the oxidizing agent, in this reaction, it would have been reduced to Mn2+. All right, just remember that. Oxidizing agents are reduced, reducing agents are oxidized. So since as potassium permanganate is your oxidizing agent, for this particular example, that is what you have to do now. Focus on each example. So for this example, X is acting as a reducing agent. What we're going to do now is look at what X is acting as in this example. So first, we said that what? For us to get a red-brown solution, it means that I2, the iodine, would have to be produced. So if you start out with the iodide ion and you get a red-brown solution, that red-brown solution indicates that iodine is produced. So if you go from iodide ions to iodine, it means that the iodide ion was oxidized. If the iodide ion was oxidized, that makes it the reducing agent. You will not have reducing agent reacting with reducing agent or oxidizing agent reacting with oxidizing agent. So if I minus in this example here, if I minus is the reducing agent, what type of agent is X?
Reducing as well, sir?
Oxidized.
Oxidized. So that is important, right? Remember, for a redox reaction, both agents must be present. You cannot have two oxidizing or two reducing agents. Oxidizing and reducing agents. So if you recognize this as the reducing agent, X will have to be the opposite. So here, in this example, X is your oxidizing agent. And the reason for that, you know that I minus is the reducing agent. So X has to be your oxidizing agent. So both agents has to be present in a redox reaction. Because remember, for a redox reaction, something must be oxidized and something must be reduced. Reducing agent is oxidized, oxidizing agent is reduced. So you won't have two reducing agents or two oxidizing agents. All right? Now, let's pay attention to Y. Remember, here we said that potassium permanganate was an oxidizing agent that makes Y a reducing agent, right? Now, when you add iodide ions to a solution of Y, what is our observation?
No, come on. No visible.
Visible change, right? So if you don't see any visible change, did a redox reaction occur?
No.
No, sir.
Exactly. And remember I said that what? For a redox reaction, both of what must be present? Both
Oxidized.
Oxidizing and
Reducing
Exactly.
agent.
So if the iodide ion is a reducing agent and you add it to Y and nothing happens, that
Oxidizing.
means Y is what?
Oxidized.
Yeah, mix it up now.
Reducing agent.
It is a reducing agent. That is why nothing happened. Remember, for a redox reaction, you must have oxidizing and reducing agents. Remember, something must lose electron and something must be there to gain it. If you have two reducing agents, you cannot have one gaining and one losing. You must have oxidizing and reducing agents. So from this experiment, let me just go back again. From the first experiment, potassium permanganate is a known oxidizing agent. You add it to a solution of Y and a reaction occurred. So potassium permanganate being an oxidizing agent automatically makes Y which agent?
Reducing agent.
Reducing agent. So Y, based on this observation, Y is a reducing agent. The same thing for X. Based on this observation, we would classify X as a reducing agent as well, because the potassium permanganate is an oxidizing agent. Now, based on this observation, we have to classify them again. So based on this observation, iodide ion is the reducing agent. A reaction occurred. That means an oxidizing agent must have been present. So since you only mix X and I minus is your reducing agent, in this example, X is acting as the oxidizing agent, right? Now for this part, you mix I with Y. Nothing happens. That is why you did not see any visible change. Could you say Y is an oxidizing agent as well?
No, sir.
No, sir.
No.
No, because a reaction would have occurred.
Exactly, right. So once you see a reaction did not take place, it means that Y is strictly what kind of agent?
Reducing agent.
Reducing agent. Y is strictly a reducing agent. If it was both, a reaction would occur here. That is why we know that X can act both as what? A reducing agent and an oxidizing agent. How we know that? X, it react with an oxidizing agent in the first example, and then it react with a reducing agent in the second example. So if it reacts with both oxidizing and reducing agent, it means that in the presence of a stronger oxidizing agent, it will have to play the role of a reducing agent. And so when it reacts with a reducing agent, then it can play the role of an oxidizing agent. So based on this observation, X can be both an oxidizing agent and a reducing agent. Any question? I feel like some of you are still here, not getting it. But it's kind of simple. Remarkable. All right, so we are to categorize X and Y. So, and then, so this was part observation 1, observation 2, and this was observation part 3. So X, for test 1, we said that X was the reducing agent. So in part 1, X is the reducing agent. And in test 2 here, it is the oxidizing agent. And then it talks about Y in part 1. And in part 1, it is acting as a reducing agent. Mhm.
Excuse me,
Right.
sir.
Yes.
So for oxidizing and reducing agents, how do you identify which one is stronger or which one is weaker at oxidizing or reducing?
All right. So you would be based on experiment, right? So just like here, let's observe what happened with X. So X down here is an oxidizing agent, right?
Yes,
But
sir, but
when you add it or when you react it with potassium permanganate, did it still act as an oxidizing? Did it still act as an oxidizing agent?
also it's a reducing agent there.
Right. That means so potassium permanganate is a stronger one.
Okay,
So
so that's when you know it's
Is that the only
wait,
time you can deduce when it's a stronger oxidizing agent or reducing agent?
yes, or well, if no, well, this one you would it
sir,
would yes,
meaning
correct.
in general, how do you identify the stronger one? Like not pertaining to the experiment, but in general.
So potassium permanganate and both and potassium dichromate, those are strictly oxidizing agents. They are strong oxidizing agents. If you react them with other substances, like they would not be able, nothing can make them act as a reducing agent. So weak reducing agents then are metals are weak or reducing agents. Well, metals are reducing agents. These are oxidizing.
Okay,
So in
sir.
terms of strength or like a rule, in terms of saying this is how you know that it is stronger. No, I'm not aware of any like statement that says like you would use this to say that they are stronger.
Oh, sir,
But
so you just have to know which one is a strong one and which one is weak. Just try to know the most common ones that
the
normally
most
come.
the most common ones are potassium permanganate and
Dichromate.
potassium dichromate. However, with see with like with group 7, the non-metals, I think there is where you can ask about their ability because non-metals are oxidizing agents. So let's look at one. I think this one will more explain how you can classify them as being stronger. Sorry. Let's use the non-metals. All right, so let's say potassium bromide, and you react it with chlorine. I'm going to just mute the mic for a second. Right, so let's say I have a solution of potassium bromide and you add chlorine just to it. This is what is going to happen. You are going to end up with a solution of KCl, and Br2. However, if you add Br2 to a solution of KCl, nothing will happen. because in group 7, this marker sticks to the board. I think what you are asking for is something like this, right? Where we say that for group 7, the reactivity, as you go down the group, their reactivity decreases, all right? Also, that means that their ability to pull electrons from a net substance, it decreases.
Okay, I fully understand now.
Right. But so you can use it in terms of like group 7 to say that fluorine is better than chlorine than bromine. But in terms of other agents now, like compounds that are not in a group, so like just like with the KMNO4 or the hydrogen peroxide, which can act as both. So like with these agents, it's based on experiments, right? So this can act as both, but this one is strictly a reducing agent. But when it comes to like a rule, it would work like with group 7. So bromine would not be able to displace chlorine, right? So it's the one above that will displace the one below it. So this reaction here, it's a redox reaction as well. And that is what will happen. So if you have Ki, let me answer the question. If you have Ki, right, and you react it, well, Br2 could have stayed, but let's say it's Cl2. What would be your observation? Anybody?
Potassium
chloride.
Well,
chloride and iodine.
You would get
oh yeah,
KCl.
a red-brown color.
That is a red-brown color. That
Yes,
is it.
sir.
Because when the chlorine displaces iodine, you would get I2, right? Now let's pick this reaction apart. What is being oxidized and what is being reduced?
Well, the iodine is being oxidized.
All right.
Chlorine is being reduced.
Yes, so let us look at the oxidation state. So for this reaction, right, we know that the potassium, we will describe potassium as what?
The spectator.
Spectator, that is correct.
Because potassium doesn't matter.
Exactly. So on this side, let us separate them. So let us make our two half equations. I minus going to form I2, right? And we start out with Cl2 and we end up with Cl minus. To balance it in terms of the atom, you would put 2 here and 2 here. Now, we need electrons, of course. So, if you are going from I minus to I2, is this being reduced? Right. Right. So, you would put what? 2 electrons here, right?
Yes, sir.
This is gaining these 2 electrons, right? So, the chlorine is gaining these 2 electrons, and so we end up with the chloride ion. So this is our oxidation half equation, and this one down here is the reduction half equation. So in terms of observation, as the person said, a red-brown solution would be formed because you would be producing I2. But if you should flip this scenario and have KCl here and I2 here, nothing will happen. Iodine cannot displace chlorine. So for this one, oh, let me ask the question. If you add this, what would be your observation? Tell me what you would write. If I ask you to write your expected observation when you add when you react KCl and I2, what would be your expected observation?
We're going to
No
process
visible
iodine.
reaction.
No visible reaction, that is correct.
Oh,
No visible reaction would take place. Because remember, I2 cannot displace chlorine. So the only way a reaction would have occurred is if I2 would have displaced chlorine, and so we would get a reaction. So if no reaction is going to take place, then you would not see nothing visible occurring. With this one, we would see a red-brown solution because chlorine would displace the iodine. Iodine is in solution, so it's aqueous. Right?
so in redox reactions, it's always aqueous or liquid, right?
We're using a solution, right?
Okay,
Of
so
iodine. So the point is here, for this one, a reaction took place and iodine was produced, and iodine of a distinct red-brown color. So that is what you would have seen. For this one, iodine cannot displace chlorine, so nothing would have been produced. No reaction would take place. And so your observation would be no visible reaction occurred.
question, sir. This might be unrelated, but if you have Fe3 plus an elemental iodine in the same solution, it will just be red-brown, right? Even though both of them present the same color.
If you have Fe3 plus,
And elemental iodine in the same solution, they have the same color. Is that what you're saying? Both of them are red-brown?
and I2, all right, which one would give iodine? I2 would have to give, but I2 would not give up any electrons. Let me see. You have
Sir,
Fe3 plus.
So I'm asking if they have the same color. So if they're in the same solution, you would not know which one.
Oh, no.
Because
Oh,
like,
that's
they have
right.
the same
Oh,
color.
it would be it, right. Yeah.
Okay, sir.
Because the color, right? Yeah. You would get basically the same color. That is correct. All right, so let's just run the next one quickly. All right, so we will do the moles questions tomorrow. All right, so below this question, we had a next table, right? So let's just complete that table and finish for the night. All right, so in this table, let me use up the next marker. So for this one, we have test, observation, and inference. So the test is we have the permanganate ion, and we are reacting it with Fe2 plus. The observation is empty, so we are supposed to do that. And for the inference, we have 2 pointers. This part, Fe3 plus ions produced. All right. So the observation section is blank. So we have 2 dots, so we must have 2 observations. And this part of the inference, we must answer it as well. So potassium permanganate and Fe2 plus is reacted. Remember earlier in the class when we did this reaction? So remember, let me put it on the board. So remember, MnO4 minus plus Fe2 plus to produce Mn2 plus Fe3 plus.
Oh, sir, so the potassium permanganate that would decolorize and iron would give its characteristic color.
Exactly. That would be your two observations. Potassium permanganate is decolorized. Or if you want to say it changes from purple to colorless, that is fine. So that would be your first observation. So MnO4 is decolorized. That is the first observation. Now, this is Fe2 plus. What is the color of this?
Green.
Green.
Green. And what is the color of this?
Red brown.
Exactly. So this will be decolorized, and what color will we see? So we will get a red brown solution, right?
So it's a green to red brown color change or something like that. We could write that as well, right?
You can put that as well. So this is decolorized, and we also a green to red brown color change. All right. Or if you want to put that red brown solution was produced, that is fine. So all I need to do is know the colors of these. So Fe2 plus is green, Fe3 plus is red brown. What is the color of Cu2 plus?
So that is blue.
Blue.
All right, so based on these observations, right? Once they saw the red-brown color change, they made the inference that Fe3 plus ions were produced. Now, if the potassium permanganate or if the permanganate ion changed from purple to colorless, which other ion was produced?
Mn2 plus.
Right, exactly. So Mn2 plus ions produced. Because remember, we had said earlier, when you see potassium permanganate changing from purple to colorless, it is going from the +7, which is purple, to the +2, which is colorless. So when you see purple to colorless, it means that Mn2 plus ions are produced. When you see the red-brown color, that means Fe3 plus ions are produced. All right, so good job on that one. Oh, sorry. Yeah. And there is one more column that we're to complete. All right, for the next column, it says we're adding MnO4 minus again, right? To SO. So it's the permanganate ion with the sulfide ion, followed by barium chloride. Now, when you get, if you pick a table, just take a time and analyze the question. All right? Let me see if they gave us anything else. Right, they gave us observations. So the first observation, it was left blank, and the second part, it says white precipitate forms. White precipitate forms on addition of barium chloride solution. All right. So two things happened. First, the permanganate ion was added to the sulfide ion. Then we added barium chloride. We are supposed to write an observation when potassium permanganate is added to the sulfide ion. They already told us what happened when we add barium chloride afterwards. For the inference, it says MnO4 minus reduced to Mn2 plus. Now, if the permanganate ion is reduced to Mn2 plus, what would be the color change?
Colorless.
It would decolorize.
It would be decolorized, right?
Sure, so sulfide has no color, so it would still just become decolorized.
Right. So I can put purple to colorless. All right. So you can say KMNO, so you can say MnO4 minus changes from purple. Sorry. So it changes from purple to colorless. I can simply say it is decolorized. All right. Now, what would be your inference for this part?
Sure.
Let me give you a minute.
Barium sulfate will be created
Wonderful.
and it's not soluble, so white precipitate.
Right. So, remember now, what happened to the sulfide ion when you react it with permanganate?
Going to create a sulfate.
Oxidized.
It is oxidized to which ion?
Sulfate.
Sulfate.
Exactly, that is correct. Wonderful. So that is why when you add barium chloride, the barium ions are reacting with which ion?
Sulfate.
Sulfate, exactly. So the question did not have to be outright, right? You are supposed to know that potassium permanganate is an oxidizing agent. When it reacts with the sulfide ion is going to be oxidized to the sulfate ion. So now in solution, you are going to have sulfate. So if you add barium chloride, and from qualitative analysis, if you are testing for sulfate ion, you actually use barium chloride. And so the barium ions will combine. So let me just do a half equation for you. So the barium ions will combine with the sulfate ions to form barium sulfate, which is an insoluble salt.
So yeah, question. Sorry, for this question, you would have to be knowledgeable about like the solubility of the group 2 sulfates to know that barium is insoluble.
No.
Oh, it says a white precipitate anyways. Okay, never mind.
Right. No, but as in from qualitative analysis, you should remember that barium sulfate is insoluble. All right. And also the next thing I should tell you, right? When they say that they add barium chloride solution, you have to remember if it is a solution, even though when you're looking at it, right, you are looking at BaCl2. When they tell you that you add a solution of an ionic compound, you have to remember that in solution, the ions are separated. So when you have a solution of barium chloride, what you actually have is a solution of barium ions and chloride ions. So even though the question said BaCl2, you have to bear in mind that the barium ions are separated from the chloride ions. So when you add a solution of barium chloride to the solution with the sulfate ion, because I also have to remember that the sulfite ion will be oxidized to the sulfate. So when the sulfite ion is oxidized to sulfate, that is when we add the barium chloride. And so the barium ions in the solution of barium chloride will react with the sulfate ion. When these two ions combine, they give you the white precipitate of barium sulfate. So that is why you will see this observation. And it even said on addition of barium chloride. All right. So that is what happens. All right. And we're going to end here for tonight. I will upload this by 9 o'clock, so you will have it to watch afterwards. All right. And whoever sent you the link, they will send you again because I will send it out. Or if you want to email me, let me put my email address and just take it off.
Okay, sir.
I can send you the link.
So this class was good. I know I feel like I could get at least 5 marks on paper 2 now.
All right, so it's real.chemist92@gmail.com. So if you want the link or the PDF file, you can send me an email. All right, and I'm going to upload the video shortly. You're welcome.